Hey guys, here are your notes on section 4.5, day 1, the properties of a rational function. So basically, so far in chapter 4, we started off by seeing what a polynomial is, how to find the zeros of a polynomial, what the graph of a polynomial is going to look like. So what's going to happen in section 4.5 is now you're going to find out, well, what happens when you take a polynomial and divide it by another polynomial, and what does the graph of that type of function look like, okay? So by definition, a rational function, and rational is just a fancy word for fraction, a rational function is one polynomial divided by another polynomial. So f of x and g of x are going to be polynomial functions. All right, so this is a rational function, and it's fine to work with as long as, what do we never want to divide by in math? We never want to divide by 0. So the only stipulation on a rational function is that the denominator, in this case the g of x function, it can never equal 0, because if the g of x function equaled 0, then we would be dividing by 0, which is an undefined operation, okay? So there it is, a polynomial divided by a polynomial. Well, the domain of a rational function is going to be really, really important, because the domain says what x values are you allowed to plug into this function, what x values are going to live on the graph of this function. So the domain plays a huge role in creating the graph and working with the function. So the domain of a rational function, r of x, is going to be the set of all real numbers, right? Because think about it, a polynomial was a very nice mathematical expression whose domain should be all real numbers. The problem is, now that we're taking a polynomial and dividing it by a polynomial, yes, the domain will still be all real numbers, except those for which make g of x equal 0. Those numbers, those x values, cannot be in the domain of this rational function. Okay? Any number that makes the bottom function equal 0 will not be in the overall domain of the rational function. Okay, just to make a note, since the rational function is, at the end of the day, a glorified fraction, we always look to reduce fractions to their simplest form so that they are at their easiest to work with. So we are going to be taking these rational functions and reducing them. But I want to make a note, when you're finding the domain is always found before you reduce or simplify. So before you cross anything out and cancel it and reduce it, the domain is always found before that, okay? All right, and then numbers that end up not in the domain, they either become a vertical asymptote or a hole. So maybe from Algebra 2, you guys remember the graphs of rational functions when you were learning them, and they have a lot of components to their graph, like a VA, a vertical asymptote, a horizontal asymptote, the holes, right? There's lots of pieces to its graph. So the numbers that are not in the domain either end up becoming a vertical asymptote or they become a hole. All right. So I just want to practice finding domains with you guys, since it's going to be a huge part of this section. So let's say you were given this polynomial function, this rational function, right? A polynomial divided by a polynomial. Let's say they wanted you to find the domain. Well, when we get into graphing these in the next section, my step 1 is called FDR. You factor, you find the domain, and then you're allowed to reduce it. So I just want you guys to get used to seeing that, because in the next section, when we start taking this function and putting his graph together, this is going to be your step 1, factor, domain, reduce. So I would look to factor it. On top, I can pull a GCF of 2 out, and then on bottom, nothing factors. All right, so we factored it. Now we find the domain. The domain would be what numbers make the bottom equal 0, right? Those are going to be bad guys. So you have to take the denominator, x minus 5, and say it's never allowed to equal 0. All right, what number is going to make this equal 0? 5. So that means x is not allowed to be 5. If you plug 5 into this function, you'll be dividing by 0, which is bad. So the domain is all real numbers except x cannot be 5. So the domain would be, as a set notation, the set of x values such that x cannot equal 5. All right, and then in interval notation, it would be any number from negative infinity to 5, union, pick up on the other side of 5, all the way to infinity. And we use parentheses to show that we are not including 5. All right, so perfect. That would be the domain. Then I would let you go back and reduce, cross out anything on top and bottom that cancels, but nothing does, so we're good to go. All right, look at this function. If you had to find the domain of this rational function, right, FDR, we would factor, we would find the domain, and then we would reduce. The top does not factor. The bottom does not factor. So really, I did not have to rewrite that, but I did. All right. Then you would find out the domain. The domain are going to be all real numbers except the numbers that make the denominator equal 0. So take the denominator and make sure that it does not equal 0. I'm going to set each factor equal to 0, which is basically saying I don't want each factor to equal 0. And then to kind of make you see this, because it's going to play a role in the future, technically x squared is x times x cannot equal 0. So then when I set each individual factor equal to 0, this x ends up not being allowed to be 0, and this x ends up not being allowed to be 0. So at the end of the day, clearly x is not, x equals 0. 0 is not in the domain of this function. But I want you to realize that you do get x cannot equal 0 2 times. So that whole multiplicity thing kind of comes back and plays in a role as to one important aspect of the graph. All right, so just take note of that. X cannot equal 0 2 times. All right, and then x cannot equal -2. Now, when it comes to listing the domain, you only have to list 0 once, but I need you to recognize that it was a multiplicity of 2 where x was not allowed to equal 0. All right, so the domain is the set of x values such that x cannot equal 0 or -2. You can just put them in a list as a set, or you could say any number from -infinity to -2, union from -2 to 0, union from 0 to infinity. Those are all the numbers that would be allowed to be in the domain of this function. Okay. All right. And then lastly, if I had to find the domain of this one, and again, I'm probably doing too many examples, so I apologize. If I had to find the domain of this rational function, I would do f d r. I would factor it, I would find the domain, and then I would reduce. All right. Now in this case, the x plus 2's would be allowed to cancel, and you would reduce to 1 over x squared. The domain is still x can't be 0 and -2. Even though -2 doesn't look bad anymore, it still will forever and always be a bad guy. All right? But that just means for the rest of the problem, I could use this reduced function when I'm working throughout the problem, but it's still -2 is not in his domain. That's why you always find the domain before you reduce, because if you reduced first, you might not thought -2 was not in the domain, and he's not in the domain. All right, so in this case, FDR, factor domain reduce, I would factor x plus 3, x minus 3, and then x squared plus 3 does not factor. So I would factor it. I did. I would find the domain, take the denominator, tell me the denominator is not allowed to equal 0, and now find the numbers that make the denominator equal 0. -3. I'll square root both sides. X cannot be plus or minus I root 3. That's an imaginary number. So that means that no real number makes the bottom equal 0, which is good. That just means since no real number will ever make the bottom equal 0, that means the domain can be all real numbers. No matter what real number you plug in, the bottom will never become 0, and that's great. So that just means that the domain is all real numbers. And then that would be -infinity to infinity. Okay? All right, perfect. So that's how we find domain. So hopefully that rings a bell. All right, we're going to be doing a lot of that when we go to create the graph, because right away you want to find out who are the bad guys, who are the numbers that you do not want to plug in to this function. All right, well, before we start talking about all of the components and the graph itself, we're not actually graphing in this section. We're just kind of learning about all of his pieces. I just want you guys to see the simplest version of a rational function. We call it the parent function. All right. The easiest version of a polynomial divided by a polynomial is the graph of y equals 1 over x. This is the mom and dad of all rational functions. It's by far the easiest, most simple rational function we could ever work with. All right. So if we're going to graph y equals 1 over x, clearly, who do we not want x to be? X cannot be 0. So the only number not in the domain of this function is 0. X can never be 0. X can be any other number, any other real number, and we'd be fine. All right, so to create the graph, I just picked some x values close to the origin to plug in to show you what the general shape of a rational function is going to be. All right, so I'm going to plug in, let's say, not necessarily in this order. We said x cannot be 0, right? If I plugged in 0, that would be 1 divided by 0. That's an undefined operation. So we're not going to plug in 0. All right, let's say I plugged in 1, right? That would be 1 goes in, 1 over 1 is 1. That's the point 1, 1. If I plugged in 2, that would be 1 over 2. So that would be 2 goes in and 1/2 comes out. All right, 3 goes in. That would be 1 over 3. That would be 1/3. So as 3 goes in, 1/3 comes out. So you can see as x gets bigger and bigger and bigger and bigger, y is getting closer and closer and closer and closer to becoming 0. but he's not actually going to become 0. No matter what x value you plug in, 1 divided by that x value will still equal something. It's just as x gets really, really big, 1 divided by a big number is going to be something extremely close to 0, okay? All right, what if I fill in the gap between 0 and 1? If I plug in 1/3, 1 divided by 1/3 is 3. So now when 1/3 goes in, 3 comes out. All right, and then when 1/2 goes in, 1 over 1/2 is 2. So 1/2 goes in and 2. So now as x gets smaller and smaller and smaller and closer to 0, that y value is going to get bigger and bigger and bigger and bigger. So right now you have a curve. As x gets closer to 0, y is getting really, really big and closer to infinity. But remember, it's never going to hit the x-axis because x isn't allowed to be 0. When you plug 0 in, an undefined number comes out. So there will be no y value that lives on the graph for when x is 0. So it's never actually going to touch the y-axis there. And then as x got bigger and bigger and bigger, the y value gets closer and closer and closer and closer and closer to becoming 0. But it never becomes 0, right? All right, what's happening over here? Well, when I plug -1 in, 1 over -1 is -1. So -1, -1. I plug in -2, 1 over -2 is -1/2. Right? And then -3 goes in, that's 1 over -3, that's -1/3. Right? So now as x technically gets smaller and smaller and smaller and smaller, that y value is getting closer and closer and closer and closer to becoming 0, but it doesn't actually become 0, right? 1 divided by any negative number, it's still going to be a number. It won't be 0, all right? So it's getting closer and closer and closer to that x-axis, all right? And then let's fill in the gap between 0 and -1. If I plug in -1/2, that's going to be 1 over -1/2 is -2. And then if I plug in -1/3, 1 over -1/3 is -3. So now as x gets closer and closer and closer to 0, that y value is getting technically smaller and smaller and smaller, right? It's going to -infinity, but it never ever is going to touch that y-axis because x is not allowed to be 0. So again, if x is not allowed to be 0, it's never going to create a y value to live on that line. All right, so now the curve is doing this. So you have this complete disconnect and you end up with 2 completely separate curves, all because x was never allowed to be this number. So since x was never allowed to be this number, there's a disconnect and it creates 2 separate curves. All right, and this will be the general shape of your rational functions, but the more changes you make to the equation, then the more changes you make to the graph, and it gets transformed and stretched and shifted and all kinds of good fun stuff. But this is the general shape of a rational function, okay? All right, perfect. All right, I just want to take note of a few things. X was not allowed to be 0. So you always want to pay attention to the behavior of the graph around a number that was not in the domain. Look what the graph is doing around that number. X is not allowed to be 0, right? So number one, I want you to notice when you approach x equals 0 from the left side. So when you approach x equals 0 from the left. So coming from the left side of 0, as I get closer and closer to x becoming 0, look what the y value is doing. As x got closer and closer and closer to becoming 0, that y value was shooting off to -infinity. All right, when you approach, let's just say y went to -infinity, right? And then when you approach x equals 0 from the right side, when I get closer and closer and closer to x being 0 from the right side, that y value was shooting off to +infinity. Okay, so you can see by the behavior of the graph around 0, one side of the graph shot off to -infinity, the other side of the graph shot off to +infinity. That's just proving that there's this utter disconnect in the graph around x equals 0. So that's actually how they prove that there is a vertical asymptote as x equals 0. All right, when these graphs are going to shoot off to these infinities like that, now you know there is a vertical asymptote. It's kind of like a brick wall at x equals 0. The graph will never exist there and never touch, and you end up with a vertical asymptote at x equals 0, okay? And then I also want you guys to take note of what is the y value doing as x got bigger and bigger and bigger. I kind of already told you, as x got bigger and bigger, right, I'm over here, as x goes to infinity, as x got bigger and bigger and bigger and bigger, the y value got closer and closer and closer to becoming 0, but it will never become 0 because 1 divided by a number will always equal something. So as x got really, really big, 1 divided by a really, really big number, it just got closer and closer to becoming 0, but it doesn't actually become 0, right? Same thing over here. Y got closer and closer to becoming 0. As x goes to negative infinity, same thing. As x got technically smaller and smaller and smaller and smaller, that y value got closer and closer and closer and closer and closer to becoming 0, but it never actually became 0, right? But it got closer to becoming 0. All right. That just proves that there's a horizontal asymptote, kind of like this line that they're approaching as x gets bigger and smaller. So that just proves that we have a horizontal asymptote at y equals 0. Okay. All right, so good. So it's just our important components that make up this graph that I wanted you guys to take note of, right? Okay. Here we go. Next page. I just want to look at one more graph, and then we'll kind of get into the nitty-gritty details of the components. All right, one more thing I want you guys to look at. So we just looked at the graph of y equals 1 over x. Now I want you guys to take the look of y equals 1 over x squared. Again, these are two very, very simple rational functions, but we can take important information away from them and apply it to the more difficult rational functions. All right, so again, if I'm going to graph this, what's his domain? Well, I definitely don't want x squared to equal 0, and that would be x times x cannot equal 0, and then that would be x cannot equal 0, and x cannot equal 0. So at the end of the day, who can x not be? X can't be 0. But I want you guys to realize that in this case, x could not equal 0 2 times. So that number technically had a multiplicity of 2, where in the original graph, x could not equal 0 just that one time, right? It had a multiplicity of 1. Well, here, x technically couldn't equal 0 2 times, that multiplicity of 2, if you will. All right, so if I create his graph, right, really quick, just plugging in some numbers around the origin, I said we can't plug in 0, so again, if I plug in 0, I would get 1 over 0 squared is 1 divided by 0. That would be an undefined output. I'm not allowed to plug him in. So now let's plug in 1. 1 over 1 squared would be 1, so 1, 1 is on his graph. 2 goes in, 1 over 2 squared is 4, so that would be 1/4. So now if you kind of notice, as x gets bigger, technically y is still getting closer and closer to 0. It's just getting closer to becoming 0 faster, right? Instead of it being 1/2, now it's 1/4, but it's still approaching 0, but it will never become 0, right? I plug in 3, that's going to be 1 over 3 squared, that's 1/9. So it's still heading towards equaling 0. It's just getting there faster and never actually gets to equal 0, right? All right, well, let's just fill in the gap really quick. If I plug in 1/2, 1 over 1/2 squared, 1/2 squared is 1/4. 1 divided by 1/4 is 4. So now when 1/2 goes in, 4 comes out. So as x gets smaller and smaller and smaller here and closer to 0, that y value is just getting bigger even faster. But I still have a very similar looking curve, right? Right, y, right? It's never going to hit the x-axis, and it's never going to hit the y-axis either, right? As x gets closer to becoming 0, it's just going to shoot off to that infinity there. All right, what's going on the other side when x is a negative value? Well, if I plug in -1, 1 over -1 squared is 1. So now, instead of -1 coming out like before, now a positive 1 comes back out because we're squaring, right? If I plug in -2, 1 over -2 squared is 1/4. So now -2 goes in and makes 1/4 come out. So now it's complete symmetry. The same thing's happening when x is positive or when x is negative. And the same thing when -3 goes in, it's going to be 1 over -3 squared. That's 1/9. So again, it's just getting closer and closer to becoming 0 that much faster, even though it's never going to become 0. All right, and then if I plug in -1/2 to kind of fill in the gap here, when x is -1/2, -1/2 squared is 1/4. 1 divided by 1/4, again, is 4. So now we end up with this symmetry, but we still end up with this complete and utter disconnect in the graph because x is not allowed to be 0. Okay, so I just want you guys to take note of a few things again, or what's happening to this graph when x can't be 0. What's going on with the behavior of this graph around this number who's not in the domain? So notice when you approach x equals 0 from the left side, so as x gets closer and closer and closer to becoming 0, that y value is shooting off to positive infinity, right? Same thing here. When you approach x equals 0 from the right side, as x gets closer and closer and closer to becoming 0, that y value is shooting off to infinity. So yes, they're shooting off to both infinity, but because we know x can't be 0, we still know there's this disconnect in the graph in between them, and they're never going to meet because x is never allowed to be 0. So there's never going to be an x value that connects these two curves. So you still end up with these two completely separate curves. All right. All right. But what I want you guys to notice is, remember how x was not allowed to equal 0 two times? So when x was not allowed to equal 0 two times, that was a number that was not in the domain, technically with multiplicity of 2, which would be an even multiplicity. And if you notice, when that number is not in the domain and it has an even multiplicity where it wasn't included an even number of times, if you notice on both sides of the graph, on both sides of that bad number, the graph shoots off to the same infinity on both sides. All right, so I don't want to go here yet. So I want you guys to realize that when you are not in the domain an even number of times, when you are repeated with this even multiplicity, the graph will approach the same infinity on both sides of that bad number. Where if you notice on the original curve, right? X was not allowed to equal 0 just one time. So now when X was not allowed to equal 0, on one side, when you approach X from the right, this side went off to positive infinity. But when I approach X equals 0 from the left, this side shoot off to negative infinity. So now when X cannot equal 0 one time in odd multiplicity, the sides of the graph will shoot off to opposite infinities around that vertical asymptote. And that's something we'll learn and be able to apply later on. And that fact will allow you to kind of sketch curves without having to plug x values in. This is just knowledge that we need to know so we can come up with the graph that much faster. So again, if the number is not in the domain, an odd multiplicity, like this only had multiplicity 1, then on either side of that VA, that bad number, the graph will shoot off to opposite infinities. But when that bad number has an even multiplicity, it can't be in the domain an even number of times, then on either side of that VA that it creates, the two curves will shoot off to the same infinity. Okay. And again, we'll talk about that more later. I just want you guys to take note of that. All right. And then last, just notice that as x goes to positive or negative infinity, we have y getting closer and closer to 0, creating that horizontal asymptote, but yet the graph never actually equals 0, right? Y never actually becomes 0. It just gets closer and closer to becoming it. All right, perfect. All right, so that kind of just wanted to get out of the way so you can see some general shapes of these rational functions. Now we're getting into like the basic definitions of what it means to be a vertical asymptote, what it means to be a hole, and your horizontal asymptote, okay? All right, perfect. All right, so here we go. Vertical asymptote, right? A vertical asymptote is, this is the fancy schmancy definition, a vertical line. All right, so the vertical asymptote is going to be a vertical line, x equals some number c, such that r of x, the function itself, the y value, goes to infinity or negative infinity as x approaches that number c, that number that is not in the domain, from the left or right side. All right. So again, it kind of easier to show it on this one. Here we had a vertical asymptote, right, at x equals 0. So when you approach x equals 0 from the right and the left, the function itself, the y value, the r of x, if you will, the f of x, will shoot off to either positive or negative infinity and show that complete disconnect in the graph. That's what it means to be a vertical asymptote, all right? All right, when you approach that x equals c, then the r of x, the function itself, will either approach infinity or negative infinity, okay, from the left or right side. If the line x equals c is a VA, then c is not a number in the domain. If you're going to be a vertical asymptote, then you must have been a number that was not in the domain. However, the converse is not necessarily true. Just because C is not in the domain doesn't automatically make C a VA. C could be a hole. I told you in the very beginning of these notes that when a number is not in the domain, that number will either make a VA on the graph, a vertical asymptote, or it will become a hole, okay? And I wrote it right there for you. The numbers not in the domain either become a vertical asymptote or a hole. So just remember, just because C is not in the domain, it doesn't automatically make it a vertical asymptote. It could end up being just a hole. All right. All right. A number not in the domain is either a vertical asymptote or a hole. Can't say that enough. All right. If R of X approaches a fixed number value from both the left and right side of C, that number who's not in the domain, then there is a hole at the point X is C and Y is f of C when you plug C into the function and get a number out. So that's the difference. If you're going to get a VA at X equals C, well, then when you approach that C value from the left or right side, the graph will shoot off to infinity or negative infinity. If it's going to be a hole, as you approach that value of C from the left or right side, then it's going to approach a fixed number value. Like if you approach it from the left and right side, if they're getting closer and closer and closer, let's say to becoming the Y value 3, that means it's a hole. If it's going to be a VA, as you approach C from the left and right side, if you're approaching these infinities, not some fixed number, then it's going to be a vertical asymptote. That's the difference between a VA and a hole. When you approach this bad number C, a VA will approach infinity, the Y value. A hole will approach some fixed number value. Okay? All right. The graph of a rational function can never cross a vertical asymptote. A vertical asymptote is like a brick wall. The graph literally cannot exist at that X value, so it will never ever be a part of the graph. You are not allowed to cross over a VA. The only reason I stress that is because when we get to the horizontal asymptotes, you will be allowed to cross a horizontal asymptote, but you will never be allowed to cross a vertical asymptote, all right? They are like brick walls. You cannot cross over or pass through it. All right. If the domain of a rational function is, let's just say, all real numbers, let's say there were no bad guys, there were no numbers that made the bottom equal 0, then there is not going to be a VA, a vertical asymptote, or a hole. There will be no VA and there will be no hole if the domain is all real numbers. Okay. All right. So for example, let's take the rational function f of x equals x minus 4 over x squared minus 6x plus 8, right? We would start, if we were going to try to create his graph, not that we're doing that yet, but step 1 would be FDR. Factor it, find the domain, and reduce it, all right? So x minus 4 does not factor. X squared minus 6x plus 8 will become x minus 4, x minus 2, right? Don't cancel anything. We factored it. Find the domain. Who can x not be? X cannot be 4, and x cannot be 2, right? Those are going to be the numbers that make the denominator equal 0. So the domain is x, I'm just going to write it not fancy, x cannot be 4 or 2. So those are the two bad guys according to this function. You would never plug them in, okay? So now that you know who the domain is, now you may reduce it. So x minus 4 and x minus 4 cancel, and it becomes the graph or the function 1 over x minus 2. So now you're allowed to use this reduced fraction for the rest of the problem. So technically, you're creating his graph now. But I want you to realize that his graph and his graph are exactly the same, or I should say this graph and this graph are exactly the same, except if we were just starting with this one, 4 never would have been bad on his graph, right? If we had just started with this one from the very beginning, 4 would not have been a bad guy, which means he becomes a hole on his graph, not a vertical asymptote. These graphs make exactly the same graph, except when x equals 4, it's a point on his graph, but it's a hole on his graph, okay? Because it canceled out of his function to make this one. And if this had been the beginning function, his graph never even had the factor x minus 4. So that's the only difference between this graph and this graph is 4 would be a completely workable point on this graph, but since this was our original function, it ends up being a hole, all right? So at the end of the day, whoever is still looking bad becomes a vertical asymptote. So since x cannot be 2, is still looking bad, that means that you have a vertical asymptote at x equals 2. But since x can't equal 4 doesn't look as bad anymore, but it still is bad, that just means you have a hole at the point x equals 4 and then whatever number you get out when you plug 4 into the reduced function. So 1 over 4 minus 2 would be a half. You have a whole at 4 1/2. Okay, and again, I'm getting a little carried away here, just getting a little ahead of ourselves, but that's what the difference. So any number that stays bad after the reducing becomes a VA. Any factor that canceled out and doesn't look as bad anymore, but still really is bad, becomes a whole. Okay, all right. All right. All right, so that's how we work with VAs and wholes. The last component that we really have to kind of put together before just finding our zeros and y-intercepts and all these other good fun points. Now you have to understand what a horizontal asymptote is going to be like, okay? What are the rules for a horizontal asymptote? All right, well, a horizontal asymptote says this. If as x approaches infinity, right, as x gets bigger and bigger and bigger, or as x approaches negative infinity, right, as x gets smaller and smaller and smaller and goes to negative infinity, the values of the function, the y values themselves, the f of x, they're going to approach a fixed number. We're going to call it L. Right? Then the line y equals L is a horizontal asymptote. So as x gets bigger and bigger and bigger and bigger, if the y values are all approaching some value, some fixed number L, that means that we have some fixed number that the y values are becoming, and that's going to become a horizontal asymptote for the graph. All right. Now, I wish the horizontal asymptote was, as I say, as easy as the VA. The VA always just comes from the bad guys in the bottom and who survived the reducing. The horizontal asymptote, who it's going to be, it literally follows a set of rules that you are going to have to memorize, all right? And it comes from common sense, so they're not that hard to memorize, but you're going to have to do it, okay? All right, so horizontal asymptote rule number 1. If the denominator degree is bigger than the numerator's degree, like here, right? This is a degree 2 polynomial. This is a degree 1 polynomial. So if the bottom degree is bigger than the numerator's degree, then the horizontal asymptote is always the line y equals 0, which is essentially the x-axis. Okay. Well, why? Why, when the denominator's degree is bigger than the numerator degree, does the horizontal asymptote become the line y equals 0? Well, think about it. If we look at this example, this polynomial function, the horizontal asymptote is basically the end behavior of the graph, right? As x gets really, really big and goes to positive infinity, or as x gets really, really small and goes to negative infinity, what are the ends of the graph becoming? What are the y values of this graph heading towards? So guys, think about it. If you plug ridiculously big numbers in, right? If x goes to infinity, you're talking like billions, trillions, like huge, huge numbers. So basically, when you start plugging a really, really big number in for x, this minus 4 and this minus 6x plus 8, guys, they become insignificant. If you plug a trillion in and minus 4, did the minus 4 really change much? No. So he becomes insignificant, right? If you take a trillion and square it, well then negative 6 times a trillion plus 8, guys, it's like nothing. It's nothing when you add that on to a trillion squared. So they become insignificant as x becomes extremely, extremely large. So you're left with x over x squared. So guys, think about it. X over x squared is like a trillion divided by a trillion squared. A trillion squared is so much bigger than a trillion. So think about it. When the denominator's degree is bigger, you're always going to have a gigantic number on bottom and then a so-so number on top compared to the bottom. So what's a smaller number divided by a big, big number always going to head towards equaling, right? This number is always going to be a smaller number divided by a huge number. That's always going to head towards equaling 0. Test it out. Take 1 and divide it by a million. It's going to be really, really close to 0. So that's what's going to happen. So if the denominator degree is bigger than the numerator's degree, then that just means you're going to be taking a smaller number and dividing it by a huge number as x gets really, really large. So that means the y value is always going to head towards 0. So the HA will always be the line y equals 0. All right? All right? Horizontal asymptote rule number 2. What if the denominator's degree is equal to the numerator's degree, right? So what if it's a degree 2 polynomial divided by a degree 2 polynomial? Well, the rule says then the HA is going to be the ratio of the leading coefficients. Okay? So think about it. Again, the horizontal asymptote is really predicting the end behavior. What is y doing as x gets really, really, really big? So think about it. As x goes to positive infinity or negative infinity, you plug a trillion in and minus 10 compared to a trillion squared times 3, this part becomes insignificant compared to the 3x squared. All right, you plug a trillion squared in plus 2 times a trillion. The plus 2 times a trillion, it becomes insignificant to what the number a trillion squared is. So again, when you plug an extremely large value in for x, you're basically left with 3x squared divided by x squared. And then what's the x squared going to do? A trillion squared divided by a trillion squared, it's going to cancel, and you're left with 3 over 1. So that means all of the y values are heading towards the number 3 over 1, which is y equals 3. I forgot to write that. All right, so that just means that your graph is going to head towards the y value of 3 as x gets really, really big. So the horizontal asymptote, the line that y is going to get closer and closer to becoming, is the ratio of the leading coefficients. Okay? All right, horizontal asymptote rule number 3. If the numerator's degree is bigger than the denominator's degree, that's the only scenario we have left, but I have to put a stipulation on it. If the numerator's degree is bigger than the denominator's degree, but only by 1 degree, so like a degree 4 compared to a degree 3, a degree 3 compared to a degree 2, right? A degree 5 compared to a degree 4. It can only be bigger by 1 degree, all right? Then there is no horizontal asymptote. All right, then there is going to be an oblique, or sometimes book call it a slant asymptote. So there's no horizontal line asymptote. This one will actually be an asymptote that is a slanted line. All right, of the form, good old y equals mx plus b. And you must long divide the two polynomials to find out what it is. Okay? All right. Well, why is that? Well, guys, look here. Here's an example of a degree 3 polynomial being divided by a degree 2 polynomial. All right? So the numerator's degree is bigger than the denominator's by 1 degree. Degree 3, degree 2. So only by 1. So think about it. As you start plugging some really, really, really large values of x in, this becomes insignificant. This becomes insignificant in a sense. I'm not actually going to cross it out because we're going to use it this time. And essentially what's going to happen is when you put a really, really big number in cubit over a really, really big number in squared, this is going to be a bigger number divided by a smaller number. Well, guys, I don't know about you, but that's how division works. You're supposed to take a big number and divide it by a small number. So normally when that happens, when we do division correctly, big divided by small, you actually have to divide it to figure out, well, what number is it becoming? So in this case, you're actually going to have to long divide these polynomials to figure out, well, what polynomial are they headed towards becoming? And when you take a degree 3 and divide it by a degree 2, you're going to be left with a degree 1, a linear polynomial of the form mx plus b. And that slanted line is who your oblique asymptote is going to be. And that's the line that your y values are going to get closer and closer and closer to becoming. All right, so you're just going to have to long divide it out and figure out, well, yeah, who is this function getting closer and closer and closer to becoming? Okay, all right, so that's probably the most annoying one because you're going to have to perform long division to figure out your remaining polynomial. All right, perfect. The only other scenario is, well, what if the numerator's degree is bigger than the denominator's degree by more than 1 degree? So like a degree 5 over a degree 3, that's 2 degrees bigger, right? Well, guys, you're still going to have a big number being divided by a small number. So you're still going to have to long divide it out, except it won't be a horizontal line and it won't be a slanted line of the form y equals mx plus b, because the difference in degrees will be degree 2s or degree 3s. So now it just means your asymptote could be a parabola, or a degree 3, a cubic graph. It just means your asymptote could be a different type of graph. And it becomes harder and harder to do those ones. So we don't really see those ones here, but I just wanted to mention it, okay? I didn't even give you an example. All right, guys, that's a lot to take in, but these are all of the components that we're going to have to put together to create the graph of a rational function. So you're going to have to know how to find a vertical asymptote, how to find a hole, how to get the horizontal asymptotes so we can start putting the graph together in the next section. All right. If you have any questions on any of this information, please reach out to me and let me know. I am more than happy to help and clarify anything. All right. Okay. I'll see you on the next notes.